Here we are. Okay, thank you guys for coming. It's a great pleasure for me to have here today Paul Carley as a speaker of the seminar. So finally we get a solar colloquium here. So Paul has been a very long-time collaborator of our institute. He has been there for many, maybe 10, 15 years. I don't know how long we have our collaboration. So he was a referee of my first paper on Mancha, and since then we are collaborating. 2006. So Paul is a full professor of mathematics at the Monash University in Australia, in Melbourne, where he also obtained his degree in 1980. And then he moved as a postdoc to UK, where he stayed for 4 years, I think. And then he came back to Monash, where he is now a researcher and a full professor of mathematics and solar physics. So Paul's research concerns, as you all know, MHD waves and instabilities in solar plasma. He has been behind many of the discoveries and many of the developments in this field since all his career. So he proposed several new instabilities in the tachocline. He proposed several works on wave theory, on mode conversion, on tube instabilities, and so on. So the list is really, really very long. So today, Paul will be speaking about the mode conversion of MHD waves in solar plasma. And okay, so we have him here.
Okay, well, firstly, I'd just like to say thank you to Elena and the IAC for hosting me again. I'm surprised they still let me back in the country. It's always a pleasure to come here and enjoy hospitality. So today, I'm going to be giving a bit of an overview of MHD mode conversion. So this isn't up-to-date research. It's not what I have done in the last year or something. It's dating back 15 years or various discoveries over that time. To give you a bit of an overview of how this operates in the solar atmosphere. And I'll be touching on a number of aspects. I may not get through everything, so I might cut something out at the end, but we'll see how far I go. So the first question is, okay, mode conversion, why? Why are we interested? What's the point? Now, the point is that waves carry energy from the sun's surface to the corona. We have lots of observations of oscillations in the corona. Those observations are basically of Alfvén or Alfvén-like waves in the corona. So in other words, transverse to the magnetic field, basically incompressible. How do they get there? How does that energy get there? We're interested in that for two reasons. One is those waves can actually contribute to the heating of the corona. So that's very important. We know the corona is hot, 1 million degrees or more. But also from the point of view of seismology of the corona, if we see waves, it gives us clues about the nature of the corona, gives us clues about the magnetic field strength, various other things, magnetic structuring and so on. So we're interested in those waves. Now, so here is a power spectrum. This is millihertz from the comp instrument, showing the power spectrum, and the blue is Doppler. The green is intensity, and you'll see that at around about 3 or 4 millihertz, there's a peak there in the Doppler. So we're actually seeing some enhancement at around that frequency in the Doppler of these Alfvén waves in the corona, but not in intensity. So that's consistent with it being Alfvén waves, because Alfvén waves show up in Doppler, they don't show up in intensity. There's no temperature perturbation associated with an Alfvén wave. And the significance of 3 to 4 millihertz is that's where the sun's P modes have their peak power. So it would appear that there is some contribution from the sun's internal seismology, the P modes that are all banging around inside the sun. There's some contribution to what's going on up in the corona. So the question is, how does it get there? So firstly, we need to understand a few things about MHD waves. Let's just do it firstly in a uniform plasma. So this is taught in everybody's first course on MHD, and I think Elena is teaching right now her students this stuff. So here's what I call the Homer-Simpson diagram. If you have an imagination, you will understand why. So this is what's more properly called a polar diagram for MHD waves. So let the x-axis here be the direction that the magnetic field is pointing. And here, this is just the perpendicular direction. And what we have, it shows you how fast waves travel in various directions. So from the origin, I can draw an arrow, say, along this direction, and the blue line is the fast wave, the green is the Alfvén wave, and the orange is the slow wave. So we've got three types of wave: fast, slow, and Alfvén. So Alfvén is just shaking of the magnetic field lines. Alfvén waves are just like if you pluck a guitar string. It's just a transverse wave, and it's magnetic tension that creates the wave. It's bouncing back and forth. Now, if I'm going off in a different direction, so if I point my wave out in this direction, for example, that's how fast the fast wave goes. This is how fast the Alfvén wave goes, and this is how fast the slow wave goes. So it's the distance from the origin in the different directions tells you about how fast they're going. Now, that's the phase speed. The group speed is how fast the actual energy is going. And you can generate the group velocity from the phase velocity in this way, which I don't have time to fully explain. But basically, if you take this wave here and then you bounce it off at right angles and come down here, you get an envelope. And this envelope is for slow waves, and it shows you the shape that if I let off a little slow-mo bomb at the origin, that's the shape that it would have as it moves out. Anyway, so that's basic MHD theory. The Alfvén speed is the magnetic field strength divided by the square root of the density. That's 4 pi by 10 to the minus 7 there. And C here is the sound speed. So those are the three different types of phase speed, of wave. So you'll notice that the fast wave actually goes fastest perpendicular to the magnetic field line, because that distance here is longer than this distance here. Three waves also have different polarizations if you look at their velocity polarization. As I said before, the Alfvén wave is polarized perpendicular to the magnetic field lines, just like the oscillations of a guitar string. It's going back and forth into the page. So think of the Alfvén wave as going into the board. The fast and slow waves depends upon the relative size of the sound speed, C, and the Alfvén speed, A. So here we've got the Alfvén speed twice the sound speed, and you see the fast wave is going in the blue directions, and the slow wave is going in the green directions. Those are actually perpendicular to each other, and that's not a fluke. So these three polarizations, the Alfvén, the fast, and the slow, all form an orthogonal coordinate system. And Here's if the Alfvén speed is low. So here the Alfvén speed is large, here it's small, and they point in different directions. So this is different from this, but they're still perpendicular. Now, that was basic MHD theory that you usually spend a couple of lectures, and I did it in 3 minutes. So if you don't understand it all, that's okay. But the point is that the solar atmosphere is not uniform. It's very not uniform. So you have 10, 15, 20 scale heights in going from the photosphere to the top of the chromosphere. So the density is dropping off a lot, and that means the Alfvén speed is increasing. Remember, the square root of the density was on in the denominator in the Alfvén speed. So as the density decreases with height, the Alfvén speed increases with height. And so that makes a big difference to the atmosphere. And in fact, the nature of waves will change as you move up in the atmosphere. So we have our 3 different types of wave: the fast, the slow, and the Alfvén. And there are mechanisms for exchanging energy between any 2 of those. So you can do fast to slow, and I'll talk about that. You can do fast to Alfvén, and I'll talk about that. And you can do slow to Alfvén. I won't say very much about that today. So here's just a view of the solar atmosphere. So here's the temperature as a function of height in kilometers. So from 0 up to 2000. Here's the transition region. We see the temperature is basically fairly constant. It doesn't change too much. But the Alfvén speed, here we're plotting the Alfvén speed for different field strengths. The Alfvén speed increases rapidly with height. So down here, the Alfvén speed is less than the sound speed. Up here, the Alfvén speed is greater than the sound speed. Each of those different colors is just a different magnetic field strength. So you can have quiet sun, you can have active regions, you can have in between. And this is the important thing. So at some height, the Alfvén speed and the sound speed will equal each other. That's what I call the equipartition height. And then as you go higher, the Alfvén speed dominates. That's crucial. Now, as I said, okay, the way this works, imagine you're on a train. Actually, I often explain it like this, but I think there are no trains in Tenerife. But you have trams, and that's a good thing. I like trams. By the way, I'm from Melbourne, and Melbourne has the largest tram network in the world. So we like trams in Melbourne too. So imagine you're on a train and you're going along a track, and there's another train going along the track next to you. And you're on this train, and your girlfriend's on the other train. You're going parallel, and you can see her. You pull the window down, and she pulls the window down, and you can give her an ice cream, provided the 2 trains are going along at the same speed. Don't try it if they're not. So if the 2 waves are going along at the same speed, they have a way of transferring energy between each other. So where you can transfer energy and or ice creams is when they're basically doing the same thing. So they have the same wavelength, same frequency. Everything looks very similar. Not exactly the same, but similar. So here's a dispersion diagram. So I think you all know dispersion diagrams. Omega squared is c squared, k squared for sound waves and so on. And you have a more complicated dispersion relation for MHD waves. And you can plot, so here's a diagram. So here's the horizontal wave number, sorry, here's the, oops, go backwards. Is the vertical wave number. No, went too far. Yep. There's the vertical wave number, and here is the height. And these lines are loci of the different sorts of waves. So this is the fast wave. So the dispersion relation, so for a given omega, a given frequency, you're on a particular branch here. So this is the fast wave. It comes down here, it goes back here, and goes down there. The fact that it goes up and does that means that it reflects here. Basically, the fast wave, if I send a fast wave up, it sees this increasing Alfvén wave, Alfvén speed, and it reflects off it, goes back down. And that's what we see in this here. The Alfvén wave, on the other hand, keeps on going upwards. The slow wave has come down here and then heads out like that. Now, as I said, where you can transfer energy is where things are almost the same. And that means where these curves come close together. And so we can see, for example, here, the slow wave and the fast wave come very close together. So that's the ideal place to exchange an ice cream or energy. And this vertical line is where the sound speed and Alfvén speed are the same. So very close to that is where you can get fast and slow mode conversion. And this is going up and this is coming down. Notice when they're coming down, this is an inclined magnetic field, by the way. If it's vertical, this would be symmetric, but it's inclined. Here, the gap is larger. Because the gap is larger, it's much harder to reach out and hand the ice cream over. So there's not much mode conversion happens here, but there's a lot that happens here. So let's have a look at this case first. So this is the fast-slow conversion. As I said, it happens near where the Alfvén speed and the sound speed are equal. Let's say we've got an inclined magnetic field. There it is. And let's say we've got the wave going in the direction of K. K here is the wave vector. And let's have this angle alpha between them. That's what I call the attack angle. So if you've got your magnetic field direction and your wave direction, and there's some angle between them, you can actually work out the transmission coefficient. The transmission coefficient is given by this formula approximately, which we came up with in about 2005, so 20 years ago now. So people were seeing this in simulations but had no understanding of it. And I managed to use a generalization of ray theory to come up with an actual analytic formula for it, which actually works very well. And the conversion coefficient is 1 minus the transmission coefficient. So this is a number between 0 and 1. That gives you how much of the wave is transmitted, how much of it is converted. And by converted, I mean converted from an acoustic wave to a magnetic wave. So if the sun's surface is basically sending acoustic waves upwards, they can go upwards and then they meet this level where the sound and Alfvén speeds are equal, and they can transfer energy into a magnetic wave. So here is a step on the way up. The acoustic wave won't be able to go all the way up to the corona. And besides which, we don't really see acoustic waves in the corona. Somehow we've got to get these magnetic waves. So when they pass through this equipartition layer, they have a chance to hand the energy over. So it's like a relay race. So here's an overview. So this is a horizontal plane. So I'm going to send in a wave. So this is carrying energy 1. So red is 1. It passes through A equals C, and it converts. Partially transmits and partially converts. Partially transmits as a slow acoustic wave. That's just basically a sound wave that goes along the field lines, and partially converts into a fast which is magnetically dominated wave, which goes up and then reflects like we saw before. When it goes through A equals C again, it again splits. Some of it goes down as a fast wave, some of it goes down as a slow wave. So we've got multiple things happening there. Now, one thing I haven't said, okay. What we'll have a look at now is the fast slow. So we've got this diagram, which is the one I just showed you. So we've sent in an acoustic wave from the surface. It's now converted itself into a magnetic wave. But that magnetic wave is going to reflect and go back downwards. We're trying to get it to the corona, so something's gone wrong. So again, we need to lean out of the train and hand it to somebody else. We need to hand it to the Alfvén wave. So we've gone from an acoustic wave to a fast magnetic wave to an Alfvén wave. So there's multiple steps in getting up to the corona. It's very hard to do it in one go. And there's another mode conversion mechanism which happens up around here, around where the reflection happens. And that converts into Alfvén waves. And if the magnetic field is inclined in that direction, those Alfvén waves go up, which is good. On the other hand, if you're going against the grain, if you've sent your wave in here and it converts to Alfvén waves, these Alfvén waves now go downward. So they don't go up to the corona. So depending upon which way the magnetic field is inclined, we're either going to get Alfvén waves sent up into the corona or sent back down to the surface. So let's just see this in operation. So here at the bottom, I've imposed a fast wave. Just we can see it coming up and traveling along in that direction. The magnetic field is inclined like that. And you see it's reflecting here. This is basically as high as it gets. It's now evanescent above that height. But it's shaking the field lines. Those shaking field lines are the Alfvén wave. And that is continuing to go upwards. Okay. Now, I should just point out that this process only works in 3 dimensions. If the wave and the magnetic field and gravity are all in the same plane, nothing happens. So you actually need, so if I've got the magnetic field like this, I need my wave to actually be going at an angle to it. And since this is a projection, I'm actually using color here to show you the velocities of these field lines in and out of the board. So it's blue shift, red shift. But we can see a lot of transference of energy into the Alfvén wave. Let's now take, so over here, I'm doing exactly the same thing, exactly the same wave, except it's going in the opposite direction. You see, this wave here is going against the grain. This one's going with the grain of the field lines. This one's going against the grain. So, and notice there's very little energy going into the Alfvén wave. Basically, all goes into Alfvén waves going downwards. This is actually an almost analytic solution. Almost analytic in the sense that it was analytic, except that I had to do an inverse Fourier transform numerically at the end. But it shows up quite nicely. So again, that's the picture that we had here. So the left frame was this, the right frame was this. Now this is some work that we did many years ago. So in a sunspot model, so Elena was running some simulations here. So we've got a wave coming up here. There's the A equals C layer. It transfers into a fast wave. And then here, we're looking at the Alfvén wave flux, and red means it's going upwards because we're going with the grain. But here, we're going against the grain, so the Alfvén waves flux here is blue, which is downwards. So in a sunspot model, we saw exactly this operating. Tell me when I'm running out of time. Okay, so what we see is this transference of energy to Alfvén waves depends upon a couple of angles. Angle theta, which is the inclination of the magnetic field. If it's purely vertical, you get nothing. So you need some inclined magnetic field. And angle phi, which, remember I said, it's a 3D thing. So if my phi is 0, nothing happens. So I've got to be sending my wave in a direction that's out of the plane. And then we can get things happening. So here's theta, and here's phi, and this is how much energy gets through to the top in the form of an Alfvén wave. So here we're seeing, in this particular model, something like a theta of 40 degrees and a phi of 60 degrees. So if this is like this, and I'm going like this, I get lots of transference to Alfvén waves. If I put a transition region, a steep transition region on the top, I get basically the same picture, but you get these wobbles, which is basically like just putting a leaky wave in a box. So you get some resonances happening. So what we see is this is all very successful in creating a multi-stage ladder for getting energy out of sound waves at the photosphere and getting them into Alfvén waves in the chromosphere. You've got to first turn the acoustic waves into magnetic fast waves and then into Alfvén waves. Two-stage process. Now let's have a quick look at flux tubes. So this is not my work. This is Pascoe et al. 2011. So it's just a cartoon I like. So think of a magnetic flux tube with Alfvén speed that's low in the center and becomes higher as you go to the edge. In other words, the density is becoming lower as you go to the edge. So the waves reflect. So this gives us another way of getting waves up high in the atmosphere. You can have a waveguide. So this is like an optical fiber that you send your favorite streaming program down the optical fiber. It's like that. So you can think of magnetic flux tubes, coronal loops, and things like that as waveguides. Waves bounce around inside the waveguide, bouncing off reflection points over here. Now, as they do, they also convert into Alfvén waves in the same way as what we've just seen. Near the reflection point, there's some conversion happening from fast wave to Alfvén wave. Let's actually see how this operates. So here is a case, let's just take a completely horizontal uniform magnetic field. And I have sent in here a ray bundle. So this is again analytic. I've sent in a ray bundle of fast waves. The red line is simply the central ray of that bundle. So this is a Gaussian bundle of waves, which I've sent in, and they're going up and they're reflecting because the Alfvén speed is increasing with height. It's the usual thing that fast waves do. The green line is where the resonance is between the fast waves and the Alfvén waves. And let's see what happens. So those coloured waves there, that's the Alfvén wave, going along those horizontal magnetic field lines. energy is coming out of the fast wave and going into the Alfvén wave. Okay, so we're seeing that in operation here, and that's also sometimes called resonant absorption. And that's what's happening in those flux tubes that I just showed you a moment ago. So that's what's happening here, where it's reflecting, and some of it is going into this Alfvén wave. And here's another view of the same thing, but this time not a spatial bundle, but a temporal bundle. So I'm sending it a fast wave pulse. It's just a finite duration fast wave pulse. It goes upwards, it reflects off the Alfvén gradient, comes back down, and it leaves an Alfvén wave there. Okay? It's a different view of the same thing. And that, notice what that Alfvén wave is doing. It's phase mixing. It's going to smaller and smaller scales as it moves along. And of course, smaller scales means that diffusion can operate. And so you can heat the atmosphere that way because you're creating very tiny scales, and all of a sudden viscosity and etc. become important. Okay, so here's a slightly more, well, this is still 8 years old. This is some work I did where I said, okay, let's take our atmosphere and let's put an ensemble of flux tubes in that atmosphere. So this is a three-dimensional atmosphere with some inclined flux tubes, all the same, which are periodic, for simplicity, for mathematical simplicity. So I've done all this basically using Fourier decomposition. So what will happen is these flux tubes will scatter any wave I send in. So I'm sending in a pure fast wave from below. And these flux tubes scatter it. So this is a view looking from the side at the flux tubes. This is a view over here looking from the top. So if I take a plane, I've got all these flux tubes coming up, and they're all arranged in a periodic ensemble. Now, here is the energy in each Fourier mode. So I've got Fourier modes M and N. So I think so M and N are integers. So 1, 2, 3. So I've got waves with a particular initial Fourier components, and then I'm adding 1 or 2 or 3 in the X and the Y direction to them. I can scatter into these other Fourier modes. And what I can see here is the energy. So the central dot is how much energy is in the fast wave, and the annulus around is how much energy is in the Alfvén wave. And here's a color scale. So red means a lot of energy. So in this particular example, lots of energy went into the Alfvén wave of the initial Fourier component. But you'll notice some energy has gone into scattered wave. So this has been scattered by 1 in the N direction, so the Y directions, Fourier component. Some here as well. Some here, that's scattered in the X direction. Here you've got quite a lot of energy scattered in the Y direction into the fast wave. So that is saying that the fast wave can actually manage to get up because it's scattered into a different wave number, which allows it to move up higher. So it's not the original fast wave which would have reflected, but because it's been scattered into a different mode, it's now able to go up. So here, this gives you a way of actually getting fast waves up higher than if you had just not had the flux tubes. However, in this example, we've got plenty of energy going up as an Alfvén wave, which is what we want. That's a bit too complicated too. Well, just look at this picture. This is looking at different modes, but this is an overall So we've initially sent in a fast wave with this much energy, or that much wave energy flux, and it loses most of its energy, and most of it goes into the green, which is the Alfvén wave. Red is the sum of all of them because all the energy is conserved. I haven't got any losses in this. So if you add up the various, the fast and the Alfvén, you get one. But yeah, so you see around this level, there is conversion happening. Okay. And here's a view at the top. So let's take a slice up at the top. We see the fast waves going back and forth. We see the Alfvén waves basically rotating around. Just giving you some polarization. Okay, so probably finish off with this. This is all linear wave theory. Everything I've done here is linear wave theory. So that mode conversion happens in the linear regime. You don't need big amplitudes. What about shocks, which we know are ubiquitous in the solar atmosphere? They're everywhere. So does this mode conversion, say from fast to slow, where the Alfvén and sound speeds are equal, does that still happen with a shock? And here we did some simulations, and here sent in a wave here, you can see a shock has formed. This vertical line is where A equals C. So this is height. And this is where the Alfvén and sound speeds are equal. So we've got this shock wave coming there, and then it meets A equals C, and what does it do? It splits. It splits into the fast and the slow wave. Exactly the same thing happens at exactly the same point. Something a little different happens though. Notice where the A equals C layer was here, just above zero. When the shock passes, it's gone up higher. What the shock does is it actually drags the A equals C layer with it for a while. So it actually has more time in this A equals C layer, which gives it the opportunity to transfer even more energy because it's pulling it along. All right, so let's have a look at the simulation here. So this is a 2D simulation. This was Jamin Pennicott, who was my PhD student at the moment, at the time. And this is just a linear case. So we've got a magnetic field which has got arcades and open field. So here's an open magnetic field. Here's arcades. Here's a neutral point. Neutral point is really interesting. And we're going to, and this purple line here, well, the two purple lines are where A equals C. The Alfvén speed equals the sound speed. So that's where we expect things to happen. So let's send in some acoustic waves from below. Here they come, just going upwards nicely, not a problem. Meets the A equals C layer, and it splits. Goes off in different directions. By the way, these different frames, we're just looking at different things. So that's the parallel velocity. This is the perpendicular velocity. This is the temperature. This is the current density, etc. We don't need to worry about the details. You can look at any one of those, basically. Now let's just let this one run again. Notice here you can see that the neutral point is like a black hole. It absorbs fast waves. It pulls them in. So it's a very good place to dissipate energy because you're pulling in a whole lot of fast wave energy into basically one point. So it becomes very intense there, and then you can use your viscosity or whatever else to absorb it. So that's very nice. That all accords with our expectation. But what happens if we now make it a nonlinear case? So we're going to send in waves of much higher amplitude, so shocks should form. Same thing, looks the same at the moment, but it's forming a shock. It's getting, oh, this is the linear case again. Sorry, go to this. Okay, this is the one I want. Same field, just a stronger wave. Notice now it's really shaking the magnetic field around because it's nonlinear. And it's actually destroyed the neutral point. This poor little fragile neutral point there thinking, oh, good, I'm going to have some dinner. And then a great train comes and crushes it. But all those things that I've been talking about are still operating. The mode conversion is still happening. Of course, it becomes more complicated because you're now deforming, destroying the magnetic structure. I won't talk about partial ionization. You've probably all heard about this from Elena. So let me just say one thing about it, that the Hall effect in a partially ionized fluid can also create Alfvén waves out of fast waves, even in 2 dimensions, even in 1 dimension, that can happen. So that's another mechanism that we've explored together in a lot of detail. So that's a further mechanism. The lower solar atmosphere is only partially ionized, weakly ionized mostly. So at least at high frequencies, this effect can also be important. But I won't go into the details of it. It's quite complicated. Okay, so I'll finish up. So there are 3 types of MHD wave, each having different properties and different abilities to reach the corona. The most important thing is that they change nature several times in moving up through the atmosphere. You can go from acoustic to magnetic fast wave to Alfvén, and then get through to the corona. So that's something that we really didn't know 20 years ago. It wasn't clear. Well, we had clues, and I'd done some work. 2008, I think I had a paper where we sort of showed this, but I don't think we fully understood the processes at that stage. We could see it coming out of the numerics. So now we much better understand the physical processes that are going on, this way that we can lean out the window and give the ice cream across to the other train. So the fast-slow conversion happens where the sound and Alfvén speeds are equal. That's almost exactly the same as where the plasma beta is equal to 1. Slightly different, but almost exactly that point. The fast Alfvén conversion happens near where the fast wave reflects. So that's typically up a little bit higher. If you've got flux tubes, you can have resonant absorption and phase mixing, etc., happening in there in a different version of the same processes. The Alfvén waves are most suitable for coronal heating. So that's why we were interested in this. We wanted to know how we could get energy from the photosphere, where it's mostly acoustic in nature, into the corona as an Alfvén wave. And these processes give you the mechanisms. The Hall effect also can do some of that. Okay, we'll stop there.
Okay, thank you very much. So anyone has any question for our speaker?
Thank you, Paul, for your presentation. I was wondering, you were talking about fast to Alfvén conversion, but it's possible the other way around, Alfvén to fast or Alfvén
Oh,
to slow?
absolutely, absolutely. All of those processes are reversible. You just reverse time and it does the opposite thing. However, what we were interested in is making the Alfvén wave. So that's what I concentrated on. If you go back 20 years ago or more, there was a lot of work done and some famous papers about getting the Alfvén waves into the corona and the solar wind by just creating them as Alfvén waves in the photosphere. There was a red herring. You know that English expression? A red herring is an issue which diverts you from the main point. There was a red herring that said, well, maybe because the ionization is so low, is so low in the photosphere, it's very hard to make Alfvén waves down there. So people were saying, no, you can't actually make Alfvén waves at the photosphere because the magnetic field is decoupled, too decoupled from the magnetic field. Now, it turns out, I think that that's incorrect. So other people, including me a couple of years ago, did some modeling of this and found, no, that's a misunderstanding. You can make Alfvén waves, but I just think there isn't a huge amount of Alfvén flux actually created at the photosphere. It's mostly acoustic, and that's in line with observations, I think. So we still do need to, and somehow we've got to explain that power diagram I showed near the beginning, where we saw a peak in the Alfvén power spectrum in the corona that was correlated with what's going on in P modes at the surface. So the P modes are basically acoustic waves. So we had to get energy out of there and put it into Alfvén. So that's the direction I'm going, but you can go both directions, sure.
Any more questions?
So can you say something about the mode conversion of gravity waves into Alfvén?
Yeah, I did some work on this a long time ago. And it still happens. I had left gravity out of the calculations here, but I did some work with my PhD student, Marie Newington, on a couple of papers where we looked at this and we saw basically the same thing happens. So basically, instead of talking about acoustic waves, we would talk about acoustic gravity waves. And a lot of the same things are happening. Now, as you know, gravity waves are very weird beasts. I mean, they seem to go in the wrong direction and all sorts of things. You think they're going up, but they're actually going down, and they're very strange. So you get differences of detail about what's going on, but I think the processes are still going to be there. But the question is how much energy is actually available in, so I think we're talking here about 1-2 millihertz, where most of the power is in the gravity waves associated with the granulation, etc. And probably it's not going to be a major source that's going to do anything for the corona. Well, actually, I'm not entirely sure about that because there is still a lot of energy at those very low frequencies up high. And maybe they play a part, but I haven't really followed that through completely. It's a question for you.
Thank you, Paul, for the very clear talk. I have a kind of a question because, of course, we know that we need to bring Alfvén waves up to the corona to hit corona. But if you listen to other groups, for example, they can tell you that, of course, there is a magnetic braiding and that what hits the corona all over. So they say, why do you care about waves at all? So what's your current understanding of this? What's the percentage?
Look, it's clear that both things are operating, I would say. So this is the AC and the DC version of coronal heating. The fact is we do see waves in the corona, which is something that we didn't until, 20 years ago. So we know they're there and they're everywhere. And the energy we can observe there is actually comparable to what you need to heat the corona and to power the solar wind. So, okay, clearly there is going to be some ohmic heating and things going on unassociated with waves. And that's going to be most notable, for example, where you're getting reconnection events and all those sorts of things. It's a complicated place. But because of this observational link between oscillations at various heights and the fact that the amplitudes are high enough to actually put a significant amount of energy in there, I think we have to look at wave heating as a serious contributor to coronal heating. And in particular, I didn't really mention it, Alfvén waves are also observed everywhere in the solar wind, in situ by spacecraft in the solar wind. We need to understand those, and they are thought to again play important roles in actually accelerating the solar wind. So all of this is important, and I think, especially as you go higher, maybe waves are playing an even more important part. Once you get to the upper corona and into the solar wind, I think waves are really playing a more important part. You're not really getting so much of the local reconnection events and things happening.
And fine. So how large do you think will be the contribution of the high frequency waves in all this? Because this is some kind of part of the power spectrum which is hard to observe, and we don't really get much information about that. But theoretically, people claim that they might be important as well. So
sorry, what component?
High frequency waves.
Oh,
so like, let's say 100
getting up
millihertz.
towards a hertz or 100 millihertz to a hertz or something.
Yeah.
Look, if I want to know that, I go and ask my friend Elena Kamenko. The thing is that at high frequency, that's when the partial ionization effects start to become most important. So, but then you've got to ask yourself the question, how much energy is actually at those frequencies? And of course, these frequencies are more difficult to observe directly. They may create some line broadening and things like that, but very difficult. So I am not sure personally. I think you would be able to give a much better answer than me on this. What we've been looking at, you've been looking at it for a while, and me just in the last couple of years, with you in general, I've been looking at how mode conversion interacts with partial ionization effects. And there's some interesting things there. Even if it's not happening in the sun's atmosphere, it will be happening somewhere. So we've identified some physical mechanisms that may be going on in other stars, even if they're not important in the sun. I suspect they're still important in the sun, but how important, I'm not sure.
Okay, I think there's time for one more question if anyone has. So if not, let's speak again. Okay.
Thank you very much. Thank you. Back your mouse, Matt. Very nice one.